want to talk about a model that's a little bit more advanced from the last one, that has some interesting dynamics and has some interesting terms in it, which we will be using a lot. It's the model of last time is a ridiculously simple model, you recall, and it's really about rabbits and the multiplication of rabbits. The state variable is x equals number of rabbits. And as I suggested, this is a case of pure positive feedback. The more rabbits, the higher the birth rate. The more rabbits are born, the more rabbits there are, and that is a classic positive feedback loop. Now, in terms of the equations or equation for this model, you recall, or let me remind you, change in x prime, equals b times x, where x is the number of rabbits. So just to remind ourselves, x prime is the change in time of the rabbit population. That is, it is measured in rabbits per year. Those are its units. And the units of the right-hand side will, of course, have to agree because it's two sides of the equal sign. So the units have to agree, and we know what the units of x are. It's rabbits. So what are the units of b? It's going to have to be the per capita birth rate because it's being multiplied by the number of rabbits. And the units of the per capita birth rate, you recall, must be 1 over years because it has to multiply times rabbits and give you years. The way to interpret that 1 over years is what it's really saying is that the birth rate is in rabbits per year. So 1 means each rabbit gives birth to 1 rabbit in 1 year. Birth rate of 2 is each rabbit gives birth to 2 rabbits in 1 year. So that's the very super ridiculously simple model. And you recall what behavior that predicted. It predicted wild, in fact, exponential growth, so that as you see, after 10 years, we are going to have a trillion rabbits. That's a lot of rabbits, and that's not a good model. And the reason why it's not a good model is because it does not incorporate limits to growth. Therefore, growth is unlimited. So we need to start to think now about, well, how do we model limits to growth? Well, what are the limits to growth of the rabbit population? The limit to growth is rabbits bumping into other rabbits in a limited space and thereby producing some kind of crowding effect. So our first stab at a model, this is not math, of course, but this is our first stab at a model, is just to write down x prime equals bx minus crowding. Now you say crowding is not math, and that's absolutely right. Always approach modeling this way. Put the words down first. Growth minus crowding plus immigration or whatever. And then you figure out how to put math on each of those terms. But you should always start with a verbal change equation. So we do that here. We wrote in the word crowding, but then the question is, what is crowding? And as we suggested, crowding means a rabbit bumps into another rabbit on the same lettuce patch. That's crowding. So in order to put math on there, we have to ask ourselves, how often will that happen? How often will a crowding event happen which amounts to asking what is the likelihood of finding two rabbits on the same lettuce patch. So let's try to figure that out. What is the likelihood of finding two rabbits on the same lettuce patch? Let's set up a very simple picture. We're going to take the total area and we're going to subdivide it into n squared little lettuce patches, one of which is shown here in green. So there are x rabbits, you see the red dots, and there are n squared little lettuce patches, each 1 unit by 1 unit. So now we want to know what is the probability of finding a rabbit in that little green box. So I want to begin by asking a simpler question. Suppose there was only one rabbit. What is the probability of finding that one rabbit in that green box, in that given lettuce patch? Well, that's pretty straightforward. You can reason directly and say, look, I'm handing out this one red ball, this one rabbit, and I'm going to drop it into one of these n squared boxes, and each box has an equal chance of getting the rabbit. So what is the chance of me pulling that green box? It's only one green box out of n squared. So the probability of me pulling that one green box is 1 over n squared. So if x equals 1, there's only one rabbit, the probability of that rabbit being in that box is 1 over n squared. But we have more than one rabbit. We have x number of rabbits. So what is the probability there? Well, we know what the one-shot probability is. And we know that if you buy 2 tickets to the lottery, you have twice as much chance of winning. So applying that reasoning, if x equals 2 rabbits, then the probability of having at least one rabbit is 1 over n squared plus 1 over n squared. 1 lottery ticket plus 1 lottery ticket equals 2 lottery tickets. So that becomes 2 out of n squared. And then clearly, if we have x number of rabbits, we have 1 over n squared plus 1 over n squared x times. In other words, the probability of finding one rabbit in a given green box is equal to x over n squared, where x is the number of rabbits and n squared is the total number of boxes. That's one rabbit. Notice, by the way, that the probability, we said the probability of having one rabbit in a little patch is equal to x over n squared. That amounts to saying x over the area, because the area is n squared boxes of size 1. So that is the area. So the number of rabbits divided by the area is also called the density of rabbits. And so we can say that the probability of having a rabbit is equal to the density of the rabbits. Okay, that's great. That's the probability of finding one rabbit in your little lettuce patch. But that was not the question. The question was, what is the probability of finding 2 rabbits in the same little lettuce patch? So in order to answer that, we have to ask a question. And the question is, what is the probability of 2 events happening jointly, A and B? So here's a picture of snake eyes in a dice roll. 2 1s. And we ask, what is the probability of rolling snake eyes? What is the probability of rolling 2 1s? Well, we use a very fundamental principle from probability theory. And that is that if 2 events are independent, then the probability of them both happening is equal to the probability of the first one happening times the probability of the second one happening, the law of multiplication of probabilities. And I stress that they have to be independent events. But the rolling of 2 dice is 2 independent events. First roll doesn't affect the second roll and vice versa. And so the probability of rolling snake eyes is equal to the probability of rolling a 1 times the probability of rolling a 1, which is, by the way, 1/6 times 1/6, and that is 1/36, or about 3%. So there's about a 3% chance of rolling snake eyes on a single roll. Now let's take that reasoning and go back and ask the question, what is the probability of one of those lettuce patches drawing 2 rabbits? That's the crowding event. So it's equal to the probability of having 1 rabbit times the probability of having 1 rabbit. By the principle of multiplication of probabilities. You have to roll the 1 rabbit and you have to roll the 1 rabbit again. So we know what that's equal to. That's equal to x over the area, x the number of rabbits, over the area, times x over the area. And that equals x squared over area squared. And so we can now say that we have found the crowding probability. The crowding probability is the probability of 2 rabbits colliding on the same lettuce patch. And we just showed that that is proportional to x squared over area squared. Now, when I say proportional, remember our definition of proportional. Y is proportional to x means that there is a k such that y equals kx. Y is a multiple of x, and k is the multiplication factor. So this very simple straight line goes through 0. That's the definition of proportional, and k is called the proportionality constant. So when we say that the crowding probability is proportional to the square of the population divided by the area squared, there's a lot of proportionality constants in there that have to do with the size of the rabbit relative to the lettuce patch, the size of the lettuce patch relative to the total area, the size of the total area. All of those factors enter into the proportionality constant in this relationship. And then there's another factor that comes in, which is that we have just defined the crowding probability. But what we really wanted to know was the crowding factor. What is the force of the crowding on the population? And the answer there is the impact of something on a population is equal to the probability of that event happening times how bad it is. Rabbits might be very benevolent competitors and they share the lettuce when they meet on the lettuce patch, or they might fight to the death, in which case the penalty for crowding is severe. So we have to define now the crowding factor is equal to the crowding probability multiplied by the penalty for competition, which could be large if it's severe and not so large if it's not. So now we have that the crowding factor is equal to this penalty P times x squared over area squared. And now we have an equation. That's the crowding factor that we were looking for. We started with x prime equals bx minus crowding, and now we are able to say that x prime equals bx minus cx squared, and that is our new model. And we keep in mind that that constant c there includes a whole lot of factors. We haven't talked about how fast the rabbits hop between lettuce patches. We did mention the size of the rabbit, the size of the lettuce patch, the penalty for competition. All of those factors are built into C. And we now have a model, x prime equals bx minus cx squared. Just stare at this model for a minute. You'll notice it has two terms. There's a positive term, bx, and there's a negative term, cx squared. They represent two different forces, two different factors that will cause change in the population. Bx in green is the birth rate, and cx squared is the crowding factor, or what we'll start calling the x meets x factor. X meets x is x squared. So we have these two factors competing with each other. And this model is a very famous model. It has a name. It's called the logistic model. And the logistic model, the growth that is predicted by the logistic model is called logistic growth. So that's the logistic model. Let's ask a question. What kind of feedback do you see in this model? Is this a positive feedback model? Is this a negative feedback model? What are the different types of feedback there? Now, the types of feedback that you see here, and we've kind of given it away with the green and the red, there are two kinds of feedback here. There is positive feedback, which is the birth rate term, the bx term. And there is negative feedback, which is the x squared term. And that's the growth limiting factor. That is the limits to growth. So we have the birth rate term and the crowding term called the logistic model. This is your take-home slide. The major take-home point of this whole development, which is something we're going to use again and again and again, is how often will an X bump into an X? How often will a rabbit bump into a rabbit? How often will a sodium ion bump into another sodium ion? How often will a molecule bump into another molecule? The answer is always the same. It's proportional to x squared, where x is the density or the concentration or the probability of having a single x. Why is it proportional to x squared? What's the proof? There's the proof. The multiplication of probabilities. You've got to draw an x, and that has probability x, because that's the density, or has probability proportional to x. And then you have to pull another x, and that has probability proportional to x. So the product of the two of them will be proportional to x squared. And that's the huge take-home point. How often will an x bump into an x? Answer, it's proportional to x squared.